Okay, so I'm going to start at the very beginning. So, why do we even need quantum mechanics? Where did quantum mechanics come from? A little bit of a sort of history lesson. And so it really starts with light. So the question is, what is light? And there was this long-standing debate, was light a particle or was light a wave? So if you go back to Newton, Newton basically observed that, if I send light through, say, a prism, it bends, it comes back out. He, learned about dispersion in different colors. But one thing he realized is light just travels in straight lines. And so as he thought about it, he decided they were particles. He called them corpuscles. But basically the idea was light are particles. They just travel in straight lines. And you can kind of figure out pretty much all of optics. You want to design a lens, you just assume light is a particle, follow the rays, they bend through the lens and come out, and it works fine. And then a few years later, in the early 1800s, Fresnel and then Young basically observed this phenomena of diffraction, where, and I guess I can demonstrate it. The more I do this, the less hair I'll have. I have to get a hair from my head. So basically, light is particles, so it has to travel in a straight line. However, I have my laser pointer here. If I shine my laser pointer on my hair, and I get it just right, you see a bunch of spots coming off to the side? Yes. That's called diffraction, and you're pretty hard-pressed to understand that as particles, right? And in fact, this is a way I can measure the diameter of my hair because the spacing of those other spots is related to the diameter of my hair. And this is a good way to measure distance, in fact. So hair is typically kind of 50 to 100 microns in diameter. And the smaller it is, the bigger the angle and the further away those spots will be. And so this phenomenon of diffraction, which you can also actually see in water waves as well. So if I took a wave, sent it through a little slit, you'd see the wave spread out when it came out on the other end. So that's a wave phenomenon. And so basically what happened was, Young did this kind of measurement with slits. It was a lot harder in the time. They didn't have laser pointers. It's a lot harder to do if you just have white light. Fresnel did a mathematical theory. It agreed. It was settled. Light is really a wave. And so by 1820, pretty much everyone thought light was a wave. And then Maxwell came along with this theory of electricity and magnetism, and it all tied together because that theory supported light being a wave. Once we understood light was a form of electricity and magnetism, everything was fine. We were in good shape. However, then what happened was the photoelectric effect. So by around the turn of the century, experiments were being done where you shine light on a surface, say some metal, and it kicks out electrons. So you're converting light into charged particles, in this case electrons. And this typically is done, you have to do it in vacuum. You have a little vacuum tube. You shine in some blue light on the surface, it emits electrons, collect them on the other side, and you measure how much current flows. And with this kind of experiment, you get what we call the photoelectric effect, which implicitly you are quite familiar with because photovoltaics is essentially related to that. In the case of photovoltaics, you don't let the electrons wander off, you collect them, and that's how you generate energy. So these experiments were being done, and then there are a number of experiments done, and you can come up with a model of what you think is happening. So why does an electron pop off a surface when you shine light on it? Well, we know light is a wave. So light is an electric field, so just think of it as it's going to grab onto a charged particle. So there's an electron sitting on the surface of this metal. And so the electron starts getting, it's feeling the wave, it's going up and down. And as I put more light in, you expect it to, oscillate larger and larger in amplitude. And eventually, probably what it's going to do is break its bond, break the spring, and come flying off. So that's kind of this classical model. There are a whole series of observations done, and we don't really need to worry too much about the details of them. But basically, so here are 5 things that were observed about, one thing you saw was if I shine in, say, red light, no electrons come off. If I shine in higher energy blue light, electrons do come in. So there's a threshold where light started coming, or electrons started coming out. To the extent that they could measure it, the electrons were emitted instantaneously. Now, if you have this model of the spring, you expect it not to be instantaneous, because I got to build up enough energy till it pops off. And the real thing that really caused problems was the maximum energy observed of the electrons coming off had to do with how bright the light was, or the intensity of the light. And if you think about it, my classical model, how bright the light is how big the electric field is. So you expect, if I turn up my light intensity, make a brighter source, I'm going to wiggle these electrons even harder, and so they're going to have a lot more energy when they come off. And what was observed is the energy just depends on the color of the light, the frequency of the light. Had nothing to do with that. So this was a real conundrum, which led to Einstein's paper in 1905, where he wrote down essentially this trivial equation, 1/2 mv squared. In other words, the kinetic energy of the electron coming off is just proportional to the frequency of the light times a constant, which we call Planck's constant, minus, this is a work function. This just is a detail about the surface. So it's a constant. It's different for sodium than cesium than aluminum and everything. When he did this, in fact, he referred to it as a heuristic point of view. Now, heuristic basically means kind of ad hoc. He didn't have fundamental physics behind it. But in writing this down, he had to assume light came in chunks, was quantized. And he essentially went back to Newton. So he called them corpuscles of light in this paper. Nowadays, we call them photons. They were named photons a few years later. But nonetheless, this was very controversial because to explain the photoelectric effect, he had to sort of ignore the fact that we now think light as waves and kind of go back to the Newtonian corpuscle view. And so this paper came out. It was an important paper, but people really, I mean, it kind of fit the data at the time. It wasn't a great fit. But no one really, it didn't get a lot of traction because it was somewhat controversial. It didn't really fit into the model. So then what happened over before we get there, and an aside. So if we look here, there's this thing called Planck's constant. So Einstein didn't invent Planck's constant. That came a few years earlier, which was also kind of the earlier, yep. It's electron volts, but in this case, it's also the voltage that I put across my plates times the charge of the electron. Energy and voltage. So it's, again, it's just an energy, yeah. Right, so in Einstein's equation here, basically he just had this Planck's constant sitting there. So where did that come from? That came only 4 years earlier from Max Planck. So he was dealing, one of the other problems that existed at the time was, what is the spectrum of light emitted from a hot material? It's what we call blackbody radiation. So as you know, if I take a chunk of metal and I get it roaring hot, it glows red, or we talk about white hot, things like that. Doesn't matter what the metal is. If I took a piece of aluminum and got it hot, or a piece of steel and got it hot, they're going to have the same color, right? So the color has nothing to do with the material. So it's some fundamental property of warm things. And so this was quite the industry, especially in Germany. People were very carefully measuring the spectrum. In other words, how much light comes out at every wavelength. And here's a plot. I mean, the sun is a good black body. So this is different curves for different temperatures. And this is the visible region here. So our sun is a black body that emits mainly in the visible. As you change the temperature, where the peak is moves around and everything. Kind of interestingly, you can ask, why do we see visible light? It's probably because we evolved in the solar system with a sun that has a temperature whose peak emission is in the visible. So if we evolved in a solar system with a cooler sun, it's possible we would see more in the infrared than we do in the visible. Yep?
I'm sorry, I must have missed it. What do you mean by peak emission?
So if I look at this plot here, so this is a plot of how much, so I take something hot. So let's take this curve. You may not read that. That's 6,000 Kelvin. It's basically, so I give you anything that's 6,000 Kelvin. It's going to be emitting, it's going to be white hot. It's going to be emitting light of all colors. And this is how much light as a function of the wavelength. And this is the visible region. And so the most light is coming out. So if you look at the sun and ask, where's the most, what wavelength does most of the light come out? Where does it peak? For the sun, it peaks right in the green. Right where we evolved our photoreceptors to be their most sensitive. So maybe it's a coincidence. It's probably evolution doing its job to work. And so if I take something cooler, so if I go down to, say, 4,000 Kelvin, then the peak is actually out here at about 800 nanometers, which is in the infrared, which we can't see with our eye, except very weakly. So if, you know, all I'm saying is if, say, I evolved in a solar system that had a colder sun, I might end up with eyes that see in the infrared rather than the visible.
Which those aliens would call the visible.
What's that?
Which those aliens would call the visible.
They would call that the visible. That's right. Yeah, to them, it's the visible. That's right. Exactly. Right.
I'm sorry, I must be really dense, but what is peaking?
I just, by peak,
Most of what? Of hottest heat of the sun?
I'm just saying the peak. Think of this as like a mountain range. There's the peak.
But doesn't the sun give off the same amount of light like all the time?
Right. I'm saying as a function of the color of the light coming out. So if I take a...
Oh, like white compared to yellow compared to orange compared
Exactly.
to... Okay.
Right. So if I disperse it into a rainbow of colors, which is the brightest? You find it's the green. So what had happened at the time was scientists were very carefully measuring the shape of these curves and then trying to predict what the shape should be. And all their kind of classical physics models didn't quite fit. Planck came along in 1901 and basically wrote down this expression. In fact, he called it totally ad hoc, an act of desperation. But what went into that was he had to quantize the things radiating in his expression. So this was really the first time that he had to like imagine nature not being continuous. So what you have to keep in mind is in the 1800s, our view of the world is a very mechanical view. Everything is continuous, right? You know, you're looking at forces and the like, and things are continuous. What this is beginning to suggest is things come in chunks. They're not just continuous. So if I keep dividing it down, there's going to be some fundamental lowest chunk. Yep.
What is that equation on the bottom?
So this equation actually describes the shape of these curves. So F is the frequency. This is in wavelength. They're related inversely. Depends on the temperature. And H is Planck's constant. And so he wrote this down. He actually made it up. He went back. He was a good physicist. He was really bothered by it, so he then spent the next few months deriving it, actually. But pretty much it was just matching a shape. It's like, yeah, let me change this. Let me change that -1 to a +1. Oh, wait a minute, I do this and it fits. Yeah. That's exponent, Euler's number, so 2.7. So 2.7 to that raised to that power.
I guess just more thing.
Sure.
2.2 is on the axis of your curve.
Yeah, it's a little hard. This is wavelength. Of the light, yeah, right. And so this is the visible region. So 400 nanometers to about 700 nanometers is what we can see. The y-axis, just think of this as how much light is coming out, brightness.
What is it? Do you mind just telling me what it says?
It's actually watts per square centimeter per angstrom. Which, again, it's the amount of light within some region of wavelength kind of thing. So I take this lava. So if you really want to think about how I would derive this curve, take the light coming off this lava, send it through a prism. You're going to get a rainbow kind of spectrum. And then just go measure how much light you see at each different color. And then record that on that curve. And that would be a spectrum. So that's one of the classic tools of physics, is doing what we call spectroscopy, which is measuring you know, the variation in light as a function typically of frequency or wavelength. Frequency and wavelength are essentially 1 over each other. So if I talk frequency, so if I talk light, we typically talk in wavelength, but frequency is just related to the inverse. So Planck did this and came up with this constant. When he actually went and fit it to the data, he got a value that turned out to be good to, surprisingly, I mean, to the actual value today within a few percent. But at the time, it's a great story. He'd been thinking about this for a while, and one of his experimental colleagues and wife came over for lunch, and the experimentalist, whose name I've forgotten, because no, it was someone much more obscure than Wien, came over for lunch and said, hey, you know, took Planck aside, you know, physicists don't do anything other than talk physics, said, I made some new measurements here, you know, way out in the tail, and told Planck about his new measurements, and then they had a nice lunch, they went home. And that evening, Planck sent him a postcard saying, yeah, I figured it out. And then he spent a few months actually deriving it. Yes, he was from PTB, which is the German version of NIST, the Standards Institute in Germany. So what happened then, so Planck had done that. Again, this was actually controversial. So even Planck didn't really think the fact that he had to make things discrete, he thought that was a calculational trick. He didn't really see it necessarily as physical reality in any way. He couldn't really explain why, he just knew it worked, kind of thing. So that.
I'm sorry, so if I'm understanding you, Planck sat down and said, there is a number missing here. And he basically figured out what that number was and called it H.
Right, so.
That became Planck's constant.
Pretty much. So basically what he did was figured out the shape of this curve, and he needed one number to explain the shape of that curve. And
it keeps working, so he's going to say, okay, it must be a constant.
Yes,
and
right.
Nobody has disproved it yet.
No, in fact, we measure it very accurately. Yep.
So when we're talking about the discrete nature of this,
Mm-hmm.
including the frequency, the fact that it's discrete is because frequency is a sine wave function. You can't really just divide it into subsections.
Well, actually, it's a little more subtle. What Planck didn't, so what Einstein did was said photons are discrete, come in chunks. What Planck actually did when he developed this, when he went back and derived it, is he said the things that are emitting light only do it in chunks. So it's a little subtle point that he quantized the radiators, not the light. But we don't need, that's getting a little too in the weeds, I think, and kind of subtle. But basically, this was really the very first deciding we have to look at things in discrete chunks. And again, it was thought to be a calculational trick. Einstein came along, and people still didn't really believe it. And then for like the next decade, basically, more and more experiments suggest that simple formula of Einstein was right. And in 1916, Robert Millikan published a paper called The Direct Photoelectric Determination of Planck's H. And he verified Einstein's equation to 0.5%. So this was really the first very careful measurement of, it's a very simple function. It's just a straight line. So basically, you just vary the energy of, you look at the energy of the electrons as a function of the frequency of light, and it's just a straight line. And Millikan did that to 0.5%. Even so, Millikan didn't really believe the physics behind Einstein. So this is a quote from his paper. Despite the apparently complete success of Einstein's equation, the physical theory of which it was designed to be the symbolic expression is found so untenable that Einstein himself, I believe, no longer holds to it. I could never actually find where that's written down. That he must have told Millikan that over a drink or something. But how else can the equation be obtained? And in fact, in this paper, Millikan tried to come up with another version which violated energy conservation. It was really kind of out there. And you know, it's kind of a fascinating story because sort of we did these very careful measurements, and then you know, the theorists came along and generated equations that fit, and they had to make their equations work, you know, assume this quantization, but they did not like it at all, and they didn't really believe it was true. And so then, in the end, Einstein won the Nobel Prize in 21. Now, of course, a lot of people think Einstein won the prize for general relativity or special relativity. If you look at his citation, it's a very interesting one. It's for services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. So, his work was done in 1905. It was really in 1960 that Millikan absolutely validated it. And, relativity was accepted by this point, but nonetheless, the photoelectric effect was seen as being a very important thing. So what is light? Is light a wave or is light a particle? One thing quantum mechanics will tell you is that light is both. And depending on what you're doing, it may behave like one, it may behave like the other. It's like, isn't there a candy bar? Sometimes you feel like a nut, sometimes you don't, right? It's that kind of version of things. So let's see, maybe I'll do this little demonstration here to show that. So as I showed you with my hair, and I'm not going to sacrifice another hair, you send light, say, through a narrow slit or around a narrow thing, and you get this diffraction pattern. So sitting here, I've got a little green laser pointer, and I have a set of very narrow slits, and if you look very carefully, you can kind of see a set of dots there. I don't know if you can all see that, but that's my diffraction pattern. So just like I showed on the board there. If you go all the way to the lowest one, Alan, right, of course the screen is, I have to get it at just the right angle that spreads it out enough that you can see it. So, you can see kind of 1, 2, 3, 4, 5 spots. That's a single laser beam just going through a very narrow slit, or pair of slits. This is probably like 30 microns or something like that. Microns, millionths of a meter. And again, hair is about 70 microns. All right, and so then what I have, and at break you can come up and look if you want, is I take some of that light, I send it out here. The rest of it I'm going to send into a detector that counts individual photons. And so you get clicks. So I have it connected to a set of speakers. So this kind of sounds like a Geiger counter kind of thing. So each one of those little clicks, so I'm blocking it now, and you can hear just the occasional click. I can turn it up a little bit. All right, so each one of those clicks is a single photon hitting this special detector, and this detector uses the photoelectric effect, and a photon hits it, it generates an electron which we amplify and makes a click. We send it to the speaker, you get a click. So lasers have lots of photons, so you're hearing lots and lots of clicks almost on top of one another. But I'm sending this light, it's looking at this interference pattern, this diffraction pattern here. So now what I can do is I can scan my detector across these spots here. And what you'll hear is, as I hit a peak, it goes way up. And then if I go to a, now I'm going in between one of the peaks, and it gets quiet again. So what I'm doing is I'm scanning through the diffraction pattern. So if you think about it, I'm going to turn this down because it's annoying. If you think about it, this experiment sort of embodies both wave and particle at the same time. It's waves because I see this interference, this diffraction pattern, but yet I'm hearing individual clicks on my detector. And so one of the kind of cool things about quantum mechanics is particles like light, like electrons, like atoms, can exhibit wave-like behavior, or they can exhibit particle-like behavior. Yep?
You said something I thought was odd. You said the lasers have a lot of photons. So that made me wonder, what about an incandescent light bulb from a flashlight? It has fewer?
That's a very good question, actually. So this laser is a power of 5 milliwatts. So we measure just like electrical power, we measure optical power. A typical incandescent light bulb is 100 watts. So there's, 10,000 times more light coming out of an incandescent light bulb. However, an incandescent light bulb, 90% of that power is going into heat. So in fact, the amount of light coming out from an incandescent light bulb is only, and this is why we're switching over to LEDs. They're much more efficient than incandescent lights. Nonetheless, the laser looks so bright because it's a single color of light, and so I can focus it, it doesn't diverge, where things that are white light sources like incandescent bulbs have a whole bunch of colors, and they're what we call incoherent, so you can't get them all to behave the same way. So in the end, when you look at brightness, you're looking at how many photons per second per area are you seeing. And so a laser, this is what makes a laser special, is you can focus it to a very narrow spot. So lasers tend to look much brighter, even though they may have considerably less photons.
Okay, thank you. I have to go there. So, why didn't we work this out sooner? If you think about water, what's water made of? Molecules that are acting like a ray. What's the difference? Sorry.
So what's the difference? Well, water molecules interact with one another, right? They're sticking together, and they're a fluid. Photons, that's one property of photons, is one photon does not in any way interact with another photon. And yet somehow they still can behave all the same as if they're in the same wave. So they don't know that their neighbor is there. So if I send one photon or 10 to the 20th photons, they don't know about their neighbors.
There wasn't good proof that atoms really existed until about this time either.
That's right. I mean, the idea of the existence of the atoms came earlier with Dalton, but it was more a chemistry and a classification thing, and that, they had come to the realization that, if I take a chunk of copper and keep dividing it down, it's still copper as far as they could see. So they had kind of started classifying things as having inherent identities. But this idea, which now, of course, we live with all the time, we think of atoms or molecules as individual discrete things, was really just coming up at that time. Yep.
So to push an analogy probably where it doesn't want to go. If you use the wave analogy going through two holes, and it comes out, and you see an interference pattern, that's because the two waves are actually interfering with one another.
Correct.
How do you contrast that with the statement you just made that photons don't interact with one another?
So each photon, and I can kind of show that, maybe I'll show this. Let me get this running here.
I've got the electron video.
Okay. Yeah, well, I have this. So Chad will reinforce some of these things, but let me just show this while we're talking about it with its funky music. So this is essentially like this experiment here. So now I have a double slit, and I send a bunch of photons through. And from the particle perspective, you shouldn't really see any interference pattern if they were just particles. Now, if I send a wave, so to really come back to your question, each photon by itself I can think of as a wave. So when it goes through the slit, the photon on the other side is a wave.
So the photon is exhibiting its own interference.
In a sense, that's right, yeah.
A single photon will exhibit diffraction.
So, depends on how you measure it. And we'll get into this a little more, but realistically, I have to do a measurement. Physics is all about what can I observe. And so what you're actually going to see is as you send this wave through, I measure the photon coming out at some place. So this is this idea that it's both a wave and a particle. If I keep, and we can skip this part for the moment. Because we'll talk about, yeah, you like that eye. So,
Yeah, right. It's on the bill. It's on the dollar bill.
So the idea is, I have, and we're going to talk soon about wave functions and things, which is how we describe things. So think of the wave function as describing this wave. The photon is going through, it goes through these slits, and by going through the slits, I modify its wave function. So now built into the wave function are these ripples, the interference pattern. But now I detect a photon. It's at some place, and so I get a little spot there. So when I send one photon through, where it shows up, it's just going to be a spot. But if I keep doing it over and over again, I'm going to build up this interference pattern. So it's a statistic, it's a probability, and we're going to talk more about the whole quantum measurement side of things. But so basically, whether this photon shows up here over here has to do with whether that was going to be a bright spot in my wave interference pattern or a dim spot.
But if you send a single photon through without observing, you get a diffraction pattern.
Yeah.
Don't observe.
Yeah, forget this observer for the moment.
You observe, if you don't observe which slit, you just observe the screen. You see it at one spot.
You're going to see one spot. Because at some point you're going to measure that photon. So let's say I put it on a camera. So some pixel on the camera is going to fire. The probability of which pixel fires is given by the wave character of the photon, but the actual photon itself is going to be a click, and it's going to be random, modulated by that pattern. Yep.
So this concept that you're putting forward in physics, that photons don't interact, is really a function of nobody having observed it yet?
No, it's sort of a separate concept. So photons not interacting is a consequence of the theory of electricity and magnetism. But it's kind of the simplest case. You don't have to worry about interactions. I could do the same experiment with atoms who are interacting weakly, and I could still see interference patterns.
You can also do it, one photon or one atom at a time. And so you send in, you know that you're sending in one photon, and there's no other photons there. You wait.
Right.
Record that one, and then you send in another single photon and repeat the experiment that way. Very much like this animation, where really only one thing going at a time.
Right. I mean, I could send a photon once an hour, once a day.
And you'll still
Eventually, I'll build up that interference pattern.
But that doesn't mean they aren't interacting. It just means they aren't interacting in the way you expect.
It means that any interaction that they have is not what's created.
Yeah.
Right.
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 Correct.
They could be interacting.
They could be interacting, but it's not necessary to generate the wave kind of character. Sure. There are no stupid questions. So what I tell my students, the only stupid question is this going to be on the exam? And since there's no exam, you're safe.
So I'm going to presume if you change the frequency of this laser, you would change the distance of the
Correct.
pattern.
That's right.
And that when you shine it through the double slit, the frequency on the other side is conserved.
Yes, that's right. Right. Frequency is conserved. They're just oscillating, so it just changes the angle. So in the end, I just wanted to, I think this was the last slide I have. Chad's going to take over. Planck's constant is sort of the fundamental constant of physics. It has this particular value, 6.6 10 to the minus 34 meters squared kilogram per second. So it's basically joules second, so it's an energy times a time, or in these more SI units here. And it's a very small number. I mean, it's kind of hard to tell from this, but meters, kilograms, seconds. But when you see a 10 to the minus 34, you realize it's a very small number. However, the fact in a way that it's not zero is the total important thing in terms of quantum mechanics. This is sort of the discrete character. This is the size of the step, the discreteness of quantum mechanics. And Planck's constant shows up everywhere in quantum mechanics, whether we're looking at Einstein's equation relating energy to frequency, or when Bohr develops his model of the atom, it has to do with the angular momentum of the electron. So it shows up everywhere. And it's the fundamental discrete character of quantum physics. I think,
Did Planck ever talk about which number he was fiddling with until he got it right?
All the other numbers.
well, I mean, he developed this formula and ended up, I mean, so what you're trying to do, right, what he was trying to do and physics was trying to do at the time was look for the universal behavior. So you measure, in that case, this black body spectrum, and you do it for different materials, and you do it at different temperatures. And first of all, you find out it doesn't matter what material it is. It gives the same shape. So that tells you there's some underlying universal character that you're trying to discover. So now I go and I measure a whole bunch of different curves at different temperatures. They all have a different shape. And what he was trying to do was say, is there one expression that encompasses all of those? And when he did that, he got an extremely simple expression that basically had, other than the temperature, which was the thing I'm varying, and the frequency, which is the thing. So remember, what you're doing is you're measuring frequency for different temperatures. So I'm measuring one, I'm controlling the other, and he basically had to have one other number, which was a constant, and he could describe all those curves. Now, what that number was, it just came out of his, development of this shape of this curve kind of thing.